So welcome everybody to the third lecture in the computer architecture course. This lecture is probably a repetition for most of you, but I would like to make sure that we're on the same page when we talk about certain instructions or instruction set architectures. So the main question, or the first question, is what is the instruction set architecture? Well, if you look up on Wikipedia, what the webpage says is that it's the part of the computer architecture related to programming. To be a little more generic, the way I would say is that the instruction set architecture specifies the set of operation codes that are supported by a particular CPU. It defines furthermore instruction format, what data types are supported, what type of storage is available, what addressing modes are available, and what is the sequencing. So just to avoid confusion, the instruction set architecture is not the hardware technique used to implement particular operations. So as an example, if you look at the Intel Pentium and the AMD Opteron processors, they support very similar instruction set architecture, but they are from the hardware perspective implemented completely differently. So the instruction set architecture basically provides you the machine commands understood by your CPU, which are typically generated by the compiler and which converts your C code or your C++ code into something that is understood by the CPU. So, although we mentioned already many of the bullets previously, what are the most relevant features for specifying an instruction set architecture? Well, the first question is what and how many internal storages are available. So, the question here is how many registers do you have? How many types of registers do you have? Because very often, or typically, you will have separate registers to hold floating point numbers and integer numbers. Second, what type of memory addresses are you supporting? We will see during this lecture what we really mean by that. What operations are you supporting? How many operands does an operation take? What are the size of the operands? How do you handle flow control issues such as conditional jumps, conditional branches, jumps, etc.? And last but not least, how is your instruction set encoded? So we will see and we will discuss for each of those bullets different options, and we will see what is nowadays the most dominant one. So before we start going into the details, I don't know, maybe some of you remember that in the early 90s, late 80s and early 90s, there was tremendous discussion about CISC versus RISC architectures. So maybe we should mention first what is a CISC. A CISC is a complex instruction set architecture, while a RISC is a reduced instruction set architecture. So in former times, where these terms come from, in former times, in the early days of computer processors, computer architects tried to encode increasingly complex operations in order to provide as much support for the compilers and to make the development of compilers simple. Furthermore, there was a fundamental belief that if you provide in hardware support for complex operations, you will speed up the execution of your application, because everything what you do in hardware is supposed to be fast, everything what you do in software was supposed to be slow. That being said, you had in the mid-90s and mid-80s, late 80s, you had architectures like the VAX architecture from Digital Equipment, which had a huge set of instructions that they supported in hardware. So really the instruction set supported by them consisted of multiple hundreds of operations. However, each instruction could take a large number of cycles. So in the early 80s, there was then a movement to go away from that approach and to have a only small set of instructions supported by your architecture, by your CPU. However, the idea was to have each of those instructions being able to be executed very fast, ideally in one clock cycle, and therefore what you had now was that a compiler had to generate, however, or had to split up complex operations into a series of very simple operations supported by your CPU. So this was a monumental struggle between fundamentally different views of the world on what a CPU should do or should not do. The question is who revealed or who won in the end? Well, the answer probably is both. So RISC architectures from the internal representation have clearly prevailed. So originally, as an example, the SGI MIPS architecture was the first RISC architecture. The Sun Spark processors, the IBM Power processors are all RISCs. The line the processor line which refused for a long time to join that path were actually the Intel with the x86 architectures, or originally digital equipment with the VEX architecture, as I mentioned. But digital equipment, as an example, in the early 90s had then suddenly their Alpha processor out, which was a very popular and a highly successful processor at the time, which was again then a RISC architecture. So RISC in the end prevailed, Intel being the only one which resisted that path for a long time. However, what Intel did was in the end a little trick. They contained, or they kept their CISC instruction set on the user level. Internally, however, a modern Intel processor also uses a very small set of commands and is basically a RISC architecture, and they have an intermediary step which is able to compile the high-level instructions generated by the compiler into the according sequence of low-level RISC-style instructions internally used by the CPU. So with that being said, let's look maybe even one step further back and discuss a little bit different options for how the internal storage, what are the options for the internal storage of different architectures. So there were three types of architectures available since the evolution of computers. The first ones actually were so-called stack architectures, where the operands, where data items were assumed to sit on a stack, and an operation was always explicitly executed or implicitly executed with the data items on top of the stack. The accumulator architecture was assuming that one of the elements had to be explicitly available in an accumulator, and as an example, we will see in a minute, if you add up a data item, you always add the data to the data item in the accumulator. The general purpose registry architectures, these are the architectures which are not neither using a stack nor an accumulator, but where you have to load data items, or where you have to make data items explicitly available to the functional unit. That's what you really have nowadays available. However, if you once again look into the instruction set provided by the Intel line, by the x86 line, they do have still a small number of accumulator operations available. So to clarify the differences between these three approaches, let's have a look what happens if you try to execute an operation such as C equals A plus B. In stack architecture, you basically have to push the elements A and B onto the top of your stack. You execute then the add operation, and the result is basically at the top of your stack. And so therefore, in order to store that element, you have to pop the element from the stack. So please note that the add operation here does not have any arguments. It is implicitly assumed that you are adding up the top two elements of your stack. In the accumulator architecture, you are loading an element into your accumulator. You add a particular value to the element in the accumulator, and you retrieve the element from the accumulator. Yeah. So one element is basically implicitly given. The second one is an explicit argument, as you can see here. In the add operation. The load store architecture, or the general purpose registry architectures, load first the elements into a register. So as an example, A is loaded into the register R1, B is loaded into the register R2. You are adding up those elements by explicitly stating the content of which registers should be loaded and into which register the result should be stored. So the notion typically is that the first argument is the register which will contain the result. If you want to write the result from the register back into the main memory, you have to use an explicit store instruction. So what are the reasons that in the end general purpose registry architectures have prevailed and have won? Well, first of all, registers are very fast to be used. You do not have the complexity of having to maintain a stack. Second, to evaluate complex operations such as what you see here, it's significantly easier to code such a complex chain of expressions in a general purpose registry architecture compared to a stack or an accumulator. Why? Because you can use registers to hold temporary results. Furthermore, because you have the ability to hold temporary results in additional registers, you are actually reducing the memory traffic, and this is beneficial for the overall execution time. So, since we agree now that general purpose registry architectures are the dominant, apologize for that, are the dominant architecture nowadays, how can we specify what element from the main memory should be used or should be loaded into the main memory? So there are various modes. There are actually a very large set of different addressing modes. We will just go here through a couple of simple examples. So the dominant form is if you use the register addressing mode, where you explicitly state the two registers which should be used for let's say an add operation. So you see, by the way, in this example here only two arguments. So we will discuss this also in a minute, that there are 2 and 3 operand versions of many operations, and once again it's a choice of the instruction set architectures which one you'll use. So the important bit, however, is that the 2 operands are given by the register names in that particular case. The immediate addressing mode, what you have here is you have one of the input registers being given by the register itself. The second argument, however, is an explicit number which you use to add up to the content of the first register. So add R4 #3 basically means add 3 to the content of the register R4. Register indirect addressing, it's typically represented by the parenthesis around a register argument. What this basically means is that the content of the register R1 represents a memory address, and you should use the data within that memory address to add up to the contents of the register R4. Using the displacement mode is actually very similar to the register indirect addressing mode. The main difference here is that you have an offset to the content of the register R1. So what this notion or what this format here really means, take the content of the register R1, add 100 to it. This will give you a memory address, and now load the data item from the memory address which is represented by 100 plus the contents of register R1, and add it to the contents of the register R4. Memory indirect addressing simply adds another layer of indirection It's typically represented by the @ sign. So what we have now is that take the content of the register R4, use it as a memory address. The resulting content of that memory address will, however, now be a memory address again. And now you can use finally the content of that address to load a particular data item. So for that last step, you have basically the register R3 pointing to a memory address. Let's call it mem1. If you look at the content of the memory address mem1, this will point you to a second memory address mem2, and that's the content of mem2 is what you're really interested in the memory indirect addressing mode. So as I mentioned, there are many more addressing modes available out there, and I don't see a benefit in going through all of them. You just need to get the idea that there are potentially different ways how you can describe which element or which data item should be used in a particular operation. Having a large number of addressing modes gives you a lot of flexibility. However, also poses the challenge onto the compiler to have the ability to use them properly. Plus, it also depends very often on certain hardware characteristics, whether, as an example, a memory indirect addressing mode can really be implemented efficiently. Which ones are used very commonly? Well, you definitely use the register addressing mode directly. The immediate mode are used. Often the displacement mode and the register indirect as well are fairly popular. For the displacement mode, one of the questions is how many bits do you really need to be able to specify the displacement over here? Well, it depends a little bit on what you want to achieve with that, but typically you use 12 to 16 bits. This means you can have, because a bit can only contain zeros and ones, the real offset or the real displacement that you can specify by that is 2 to the power of 12 or 2 to the power of 16 from a given memory address. The size of the immediate field for immediate addressing, so if you want to add a constant to a particular register, is typically in the range of 8 or 16 bits. So you have, of course, some limitations by limiting the size of those fields, but realistically this turned out to be sufficient. So we hinted already at that. One of the other questions that is occurring is whether you want to express an add operation to have 3 arguments or 2 arguments. So for the 3 argument version, like let's say add R3, R2, R1, you have basically 2 registers which tell you the input, where the input data comes from, and you have 1 register where the result will be stored. For a 2-register format, what you can do is you can have add R2, R1, where basically you have to take the content of R2 and the content of R1, add the data items up, and the result will now, however, be stored in the R2 register again. So one operand is used basically for both as an input register and to store the result. If you take one step further, you could also ask, remember that we've talked of the various addressing formats. Some of them, of course, point to a memory address. The question is now, how many of those 3 operands do you allow to really be a memory address? Or how many of the up to 3 operands? So for pure load store architectures, often also called register-register architectures, you have typically 3 operands and none of them is allowed to be a memory address. You have after that also so-called register memory architectures where you are operating with 2 operands, out of which 1 is allowed to be a memory address. The divx architecture, which I think we've mentioned already a couple of times, had actually support for both 2 and 3 operands operations where both, respectively all operands, were allowed to be to contain memory addresses. I am not aware that today somebody still uses those type of operations, but they used to exist. For the first two, however, you still have architectures out there using both type of operations, like pure register operations as well as register memory operations. So as an example, the Intel architecture, the Intel x86 ISA does have support for actually both 3 operands and 2 operand instructions. Another issue arising when dealing with memory, when defining the behavior of an instruction set architecture with respect to memory and to addressing, is what is called memory alignment. So the idea here is that typically the data types that you are supporting can only be stored starting from a certain memory address. So to give you an example, if you have a double which we call C here, a double is very often 4 or 8, is typically 4 or 8 bytes. The question is now, are you allowing the system to start such a double element at the address 0, 1, 2, 3, 4, etc., knowing that the data item is 4 bytes. Most architectures today are flexible, but unless you are following the rules of memory alignment, you will see a performance penalty. So the alignments typically have to follow the size of the data type. So let's not start with 1 byte for the sake of simplicity, but let's start with 4 byte words. What we have here is basically, if you look at this line and you have a 4 byte word such as an integer value, you can start the 4 byte word at the element 0. You cannot start it at the element 1 because this would be a misaligned word. You cannot start it at the element 2 or at the element 3. However, you can start it again for a 4 byte word at a multiple of 4. The same for an 8 byte word. You can basically start the 8 byte word at the address 0 and any address that is a multiple of 8, but you cannot start it in between because this will lead to misaligned memory accesses. Now, there is at least one architecture out there that I know about. These are the Sun Spark 4 processors, which if you would try to access a double, as an example, from a memory address which is not a multiple of 8, your program would fail. On Intel architectures, typically what happens is that if you have a misaligned memory access, it works. You have to pay, however, a performance penalty, because in reality what happens underneath the hood is that the system has to load 2 double words, and it has to do some shift operations in order to get to the according elements. So that's why we say here, in the best case, things work, but it requires, but you will have a performance penalty if you are accessing data items which are not aligned according to the rules imposed by your instruction set architecture. In the worst case, the system does not allow it and you will have a failure. This will lead to an error. The next question is, now we know that we might have a large number of potential operations. We might support different addressing types, different type of data types. How does the instruction set architecture now define whether we want to add up to floating point numbers or to integer numbers, or whether we want to add up to double double precision floating point numbers or single precision floating point numbers. You basically have now two different choices. You can either encode it into an opcode. What do we mean by that? If you execute, let's say, an add operation on two registers, this implies that you are using integers. If your instruction is called add.f, then it's a floating point number. If the instruction is called add.lf, it's a long float, a double word instruction. So in that case, you are basically the name of the instruction describes already the data type to be used for the particular operations. Alternatively, what you could do is you could have an additional argument to the instruction, or to the instruction itself, or to the operation itself, which indicates the type of operands that you would like to use. What are common type of operands? Well, you have characters, which are 8 bits. You have half words, which are 2 bytes or 16 bits often. Words, which are 4 bytes or 32 bits. Single precision floating point numbers, which are 4 bytes and 32 bits, and double precision floating point numbers. So these are common values, but are not necessarily always given. So there are a number of architectures out there where a word was, as an example, 8 bytes. This was, to give you an example, the Cray T3E, which used a digital equipment alpha processor, had 8-byte words, and so on. Formerly, before we had 32-bit processors out there, you also had architectures, as an example, if I remember right, so I'm sure the 286 architecture from Intel, the double was a 16-bit processor where the double precision floating point number was only 32 bits. So the instruction set architecture has to define the type and the length of data types that it supports. Regarding the encoding of characters, you noted that here we are assuming that it's 8 bits. Now, as probably most of you know, that's what is called the ASCII code. Many of the modern processors also have support for Unicode, which has been introduced with actually Java, where a character is actually represented by 2 bytes. How are integers encoded? Well, so that's hopefully also something that you've learned in the undergraduate computer architecture course that you had. Basically all computers nowadays use 2 complement binary numbers. How are floating point numbers encoded? So what does the encoding actually mean? The encoding means how do you interpret the 32 bits available for, let's say, a single precision floating point number. You will have somewhere the notion that one part represents the exponent and one part represents the mantis. How many bits you are using for which of those are actually defined in what is called the IEEE standard 754. There are a number of other standards out there. So to give you an example, IBM had for a long time its own standard. NEC has its own floating point representation. Cray had its own floating point representation. But in the end, right now, it looks like things have converged towards the IEEE standard 754. So this defines on how, not just how data are represented, but also what has to happen in case of certain exceptions, in case of certain problems. Like what is the result if you have a division by 0? Yeah. One of the notable things which is not defined by the IEEE standard 754 is that if you are using something like a long double data type, that's actually not defined. Neither operations on long doubles are defined, nor the preset representation. And if you look around on different architectures such as Intel Pentium or Intel Itanium or IBM PowerPC processors, they do have in fact very different representations for long doubles. What are the type of operations supported by the instruction set? Well, the most popular and clear ones are arithmetic and logical instructions such as add, subtract, and or multiple divide operations. You also have data transfer operations such as load, store, and move. You have control instructions such as branches and jumps, or function calls, or returning from a function calls. You have certain system level operations which are required, as an example, for virtual memory management. In case you have, as an example, a page fault, the system has to now load a page from the hard drive into the main memory. Last but not least, you also have floating point arithmetic instructions to add to floating point numbers, etc. So these are basically available everywhere. You have of course some more instructions often available, such as string instructions. So the Intel x86 instruction set has a large number of operations to move strings, to compare strings, etc. available, which you could use. For those of you who are familiar with operations in graphics, there are of course also instruction set architectures out there to manipulate pixels, vertices, to handle compressions, etc. But those are not necessarily available on all types of processors. Very often they are only available on specialized processors. Something interesting, however, that I would like to point out is that there are some processors out there which have hardware support for adding, multiplying decimal numbers. So the reason why you might need that is actually for financial institutions. It's very easy to, so that's required by some financial institutions. I don't know whether you remember the undergraduate course on computer architecture where you defined or where you discussed how binary additions or binary multiplications, etc. work. But it's very easy to construct an example where you add up two decimal numbers and the outcome or the result of the addition if you use a 10-base system is clear. As soon as you convert, however, the numbers to the binary representation and you add them up using the binary add operation, you convert afterwards the result back into the decimal system, the result suddenly is not the same. It's fundamentally different. Now this is probably fine for most of us and for most of the operations, but for financial institutions that's often not the case. So they use there are certain circumstances where they use processors which have in fact support for decimal numbers and for decimal operations. It's not very widespread, but they are available. So let's talk also a little bit more about flow control instructions. What are flow control instructions? Well, if you think about the regular code sequence, what really happens is that the compiler generates a series of operations that have to be executed by the processor, and the processor will really take one instruction after the other and execute it. An important notion what you have there is the program counter, PC. That's the address of the instruction currently being executed. And what typically happens is, if you think of the address being a 32-bit number, you read the program code at location I, and then you increase I by 4 to read the next instruction from the main memory. The question is now, however, what happens if you have an if statement in your code? Then you might not have to access the instruction at location I plus 4, but you might have to do something entirely different. You might have to jump to a different region in your code. So the question is, what type of flow control operations does the instruction set architecture support? So the four typical operations are conditional branches, jumps, procedural calls, and procedural returns. What are the options to define where to go for one of those flow control operations? So there are two alternatives. you can either try to specify an absolute value which you add to your current program counter. That's called a PC relative mode. Or you can use register indirect addressing. Basically what happens there is that your conditional branch or your jump will contain the address or the name of your register, and this register will contain the target address where to continue the execution. So PC relative could be a little faster because you do not have to have the problem that you have to read or load first another register in order to see where to contain execution. Register indirect is a little more flexible. So register indirect in fact has to be used every time you cannot determine the outcome of the condition using a single displacement. So to give you an example, when you have a case switch statement in your code, the condition variable can in fact point to multiple locations. So you cannot take a single displacement value which potentially you could add to the current program count. You need to go through these separate indirections, so therefore your code can update the register containing the next program counter, and you basically just jump to that address to load the address where you want to continue. The same occurs if you have virtual functions in C++, where the function that you really execute depends on the operands or the input values that you pass in. The same happens for function pointers in C or whenever you use dynamic shared libraries such as DLLs in Windows or .so files in Unix. So register indirect is not something that you can avoid. It will definitely be there. So one further question arising with flow control instructions is what happens whenever you call in another procedure. The reason this question is different than the question of determining where to continue is because a function or a procedure or a method in object-oriented languages will typically have some local variables where you basically need to save the state of those variables. And you have actually two options on what you can do. The question is the procedure that is calling the other subroutine responsible for saving the contents of the current temporary variables or whatever. That is called the caller saving. Or is the procedure that just has been called responsible to make sure that all the registers which contain now contents of variables of the previous procedure, whether he has to store the according values in order to be able to restore those values after this procedure or this function has finished. So depending on who is doing that, we're talking about caller saving or callee saving. Furthermore, what you also need to agree on is how to access global variables. Yeah. And by the way, the minimum that you always will have as a global variable is, in that case, the return address. Because once the operation or the function has finished, it needs to know at what address you have to set the program count in order to be able to return and continue the execution from the previous location. So how is actually saving those registers when implemented? There are actually multiple options. In former times, many of the instruction sets architectures or of the CPUs have had special instructions to store a large number of registers at the same time. That's typically not the case today. Today what really happens is that the compiler on every function call explicitly introduces store instructions for registers that it knows that it will need the content afterwards. Last but not least, one more important bullet is how do we encode the overall instruction within the instruction set. So we can have 2 or 3 operand instructions. We can have operations which might contain a tag to indicate whether we want to add up to floating point numbers or to integer numbers. And the question now is we have different addressing modes, if you remember back, with immediate addressing, displacement, etc. The question is now, how do you use a certain number of bits for an instruction in order to specify all of those options? There are two ways on how to do that. You can basically introduce a fixed encoding scheme where you take into account that some of the fields might not always be used properly. So as an example, the first RISC architecture, which has been released, the MIPS architecture, the MIPS processors, had a fixed encoding scheme where the first, n bytes contains the operation code and the other two address field. And there was no deviation from that field or from that format. Everything was the same. I'm not sure how much it was. I think it was like 48 or 64 bits. Yeah. On the other hand, you had the approach supported by most CISC processors, where you have, in fact, a variable length instruction. The first bit being representing the operation, or the first bits representing the operation and the number of operands. You had additionally address specifiers, which tell you what type of addressing you are really using, followed by the address field, etc. Now, once again, keep in mind that you might have operations which take 2 arguments and operations which take 3 arguments. What the variable encoding really gives you is that you are definitely not wasting any bits, because you will never have unused bits in your instruction. On the other hand, you have to take into account that because that the length of the operand and the length of the instruction can vary dramatically, and by dramatically I really mean a lot. If you look at the I don't remember the precise maximum length in the x86 architecture, but the variability was between the shortest possible instruction and the longest possible instruction was tremendous, with more than a factor of 2. Was way more than a factor of 2. So this, of course, adds also complexity to your hardware, because depending on the first couple of bits, you have to do different things on how you interpret the subsequent bits. While for fixed encoding, you always can execute exactly the same instructions. You always know that the first address starts at bit number, 24 or whatever. Yeah. So that being said, we discussed now basically all components which are really relevant to define a instruction set architecture. The following 2 slides just give a simple example for an instruction set architecture, namely for the MIPS 64 ISA. So MIPS was the processor generation used for a long time by Silicon Graphics. The MIPS 64 is the architecture which has support for 64-bit data types. So let's have a look very briefly. So it's a load store architecture, and it defines that the processor has 32 general purpose registries for integers, each of those registries being 64-bit wide. MIPS 64 also defines furthermore that the register R0 cannot be used for calculations, since it always contains 0. Why do you need that? We will actually see a number of examples where this helps you for certain calculations or for certain immediate addressing operations. It also defines that you have 32 floating point registers, each floating point register being 64-bit wide. The question now is, what happens if you are dealing with 32-bit floating point operations, since you are having 64-bit wide floating point registers? Well, if you are only having a single 32-bit floating point instruction, you are basically not using half of that register. However, the MIPS64 architecture also has specific instructions on how to operate two floating point operations within a single 64-bit register. That's, by the way, also something which has been later on introduced by Intel in the SSE instructions. Yeah. The data types supported by the MIPS64 ISA are 8-bit bytes, 16-bit half words, 32-bit words, 64-bit double words, and 32-bit and 64-bit floating point data types. So please note that there are no 16-bit floating point numbers, right? Addressing modes supported by MIPS64 are the immediate and displacement modes, additionally to the register addressing. The displacement field and the immediate field are both defined to be 16-bit wide, which basically limits the constant that you can add to any of those addressing modes. The register indirect addressing is accomplished by using now the special register R0, since we know that it always contains 0. So what this gives you is that basically you have n of a register number, right? If you know that if this n is 0, then you have actually register indirect addressing. If this n contains a value, you have the displacement addressing mode. So using this trick, they managed to support one more addressing format without having to do anything in hardware additional to that. So I would not like to go through those examples, but what I would ask you to do is I would ask you to go at least through the first couple of them and make sure you are fine and you are familiar with the terminology on what really, as an example, this load instruction here means. Where will the result be added? Where will the data item be stored? What is the address being used to load the according operation, etc. With that being said, I hope that we are on a common page with respect to instruction set architectures, that you are clear on what are the options for all the different arguments, etc. And we can now, in the next lectures, simply use, let's say, an LD or an add operation with the according registers, and we do not have to discuss at that point anymore what those arguments really mean. Thank you very much.